Warm greetings. Welcome back to Physics Clinic at the Red Rose Academy. Today's topic is we are going to learn about the conductance of the electrolytic solutions. Now, here, two glasses of water. They look completely identical. If it is connected with bulb circuit to each one, do you think the bulb will glow the same way in both? Any guesses? Okay. So let's find out from this.
All right, science family.
See, listen.
We've been learning about a
So
lot of
sugar
different things about
and salt, both the solutions are here. Okay.
understanding the difference between
See, actually, let's find out the answer because the answer is going to change how you think about your own body, your phone charger, and even that RO water purifier at your house. Okay. So right now in glass one, you might have seen the sugar solution, and in salt in the next beaker. Okay. So add a spoon of sugar and salt in both the thing. So you'll be getting all these steps. Okay.
So right in front
We
of me
are going
here,
to add now
sugar
sugar
and salt.
and then salt.
Now,
Okay. So,
ionic compound.
and then
Let's
there
explain
is
that
a,
in the middle. That means that it's an ionic
the
compound.
sugar, the
Now,
formula of the sugar and the
one sodium
formula of the salt. Let me come to that.
I'm going to take my
So first of all, you can look into
I'm going
it.
to dump it in my
So
bowl.
salt is now added.
My glass stirring rod,
Okay.
and I'm going to
So
dissolve
salt
that
and
glass
sugar now
into the
stir
water.
up and it is fully dissolved.
Let that
Okay.
sit. Now I'm going to take
So it
my
looks like the
beaker.
same.
I'm going to take it in my empty
If
beaker
you
that just
see,
has water in it, and I'm going to add when we're
then
rehydrating ourselves
see.
because those ions can help
Okay.
with proper muscle
And
function.
now what is
This
happening?
is important. Sodium,
We are going to
calcium,
see.
all day like a local
Okay.
tournament in volleyball or
Which one glows?
country run
Okay.
race.
In which
You mentioned about
you're dipping the bulb with an
what I
electrode
have here is an
with electrodes,
apparatus.
two
It has a light
electrodes.
bulb.
So now the salt solution and sugar
You can
solution is
see
acting as an electrolyte solution.
the thing
Now
is,
we are going to check the conductivity of the electrolyte solutions. Okay.
there is
So
a
these
light
two
bulb,
electrodes are
but
positive and negative
in the
electrodes
circuit for those of you
connected with the
who are
bulb.
left.
This is the output.
What I'm going to do is
So you have to
I'm going
check
to put
first with the sugar
water
solution.
inside the sugar
Okay.
water to start. If the sugar
Sugar
water
solution is
doesn't
completely dissolved. This is the
go
completely
on. So let's see if that happens.
dissolved one. Now you check no light. Okay. The bulb is not glowing.
So, an
Okay.
explanation
What is the
is
reason? Students
sugar,
guess.
which
I'll
are
ask you.
covalent compounds, right?
Then
It's a
it
molecule.
is now dipped into
When they
the
dissolve in
salt
water,
water.
again,
See
electricity,
how the bulb glows.
and lo and behold, it does.
Seriously, right?
Do you see that?
So it shows,
When I put the light
okay, the
bulb
conductance of the electrolytic
shows
solution. How you are
inside
saying salt is an
the
electrolyte,
amount of
sugar
electricity.
is not an electrolyte.
So
Okay. So this particular, both sugar and salt dissolved. So why did only one glass light the bulb? So that is the idea. So this is the entire chapter in one sentence. I can say current needs charge carriers that are free to move. So I will explain you how it is formed. For example, if you take what is that? First we saw salt water, right? So salt water conducts electricity, right? Because it contains free moving charged ions. What are the charged ions? Na plus and Cl minus, right? So both it consists of both. And then we are going to see sugar water. In sugar water, it does not conduct because sugar dissolves into neutral uncharged molecules. So here the simple example I'll let you know. So what is the salt solution? It consists of sodium chloride, and it is now splitted into two ions, Na plus and Cl minus. Okay, so these ions are the free charge carriers. So these two set up in terms of what? Na plus and Cl minus. For example, we can say the table salt is with the ionic bonding. So transfer of electron takes place. Okay, it is basically the water molecules break these ionic bonds apart when salt dissolves. Okay, so this is what happening, and the separated ions freely. I mean, it roam. We can say it is moving freely throughout the solution. So these mobile charges move towards opposing electric poles. Okay, when the voltage is applied, then there is a current flow. You know all these stuffs. Okay, so there are Na plus and Cl minus ions, and then water also converted into ions, H plus and OH minus ions. You might have able to see all these things. Okay, so right now what will happen? These ions gets, see, this is high conductivity electrolytic solution. This is strong electrolyte. This one is weak electrolyte. In this, you can able to see very low conductivity of electricity. What happened in sugar? Its sugar consists of C12H22O11, right? It is held together by covalent bonds where atoms share electrons. There is no transfer of electrons. There is no movement of free electrons. Here, what is happening? The mutual sharing of pair of electrons takes place. So it is held up together. Okay. So molecular dissolution, if you talk about water, separates the sugar bulk into individual sugar molecules, but cannot break the molecule itself apart. That is the big thing you can able to see. Okay. It doesn't break the molecule, but it separates the sugar bulk into individual sugar molecules. Okay. No charges here. That means the dissolved sugar molecule remains completely neutral. There is no current, right? The current is due to the movement of the charge carriers. So that you know. We can able to understand the type of bonding. Here ionic bonding and here covalent bonding, right? Here also ionic bonding, but this is weak electrolyte. Okay. And you can able to say which one is strong electrolyte, which one is weak electrolyte. Okay. Electrical conductivity is very high in strong electrolyte. Okay. So you must know how the conductance of electrolyte or electrolytic solutions happens. Okay. This is what we are going to see in this particular topic. Let us move on to the so students, let's move on to your topic. So conductance of electrolytic solutions. Conductance is just how easily current flows. I want to give you the three major ideas which is involved in it. Take a note of it. Okay. So conductance is just how easily current flows. That is conductance. The electrical equivalent of a wide empty road versus a traffic jam. Like that. Okay. So like this you can equate. Then concentration also matters. But in a surprising way, as you dilute a strong electrolyte like NaCl, each individual mole of ions actually conducts better because the ions have more room and a less crowd drag from each other. So this is molar conductivity increasing with dilution. So that's why. Can you able to get the answer? So if you dilute a strong electrolyte like an NaCl, each individual mole of ions actually conducts better because what happens? The ions have more space, okay, and less crowd drag from each other. So this is the reason. Then weak electrolytes like acetic acid, water, we saw, vinegar, that is acetic acid. It is, I can say, concentration matters, we saw, right? So only a small fraction of molecules breaks into ions. So dilute them enough and suddenly almost all of them dissociate. Molar conductivity shoots up dramatically. This one curve difference is what you'll be asked in JEE or NEET paper. Okay, this one curve difference. You might be asked all these things. Okay, so dip electrolytes in weak electrolyte like vinegar next to the salt water, that is strong electrolyte. Bulb glows dimmer in vinegar at the same concentration. So we saw that visual proof also for salt and sugar. The same for vinegar also you might have seen. For vinegar, the bulb glows very dimmer, okay, when compared to the salt solution. So we'll see. Similarly, we can able to understand for weak electrolytes, you cannot directly measure the maximum possible conductivity. The graph refuses to behave. So we are going to see that also. Okay. And yeah, in this. Okay. So we are going to see this. Okay. And we are going to see Call-Rush law. Okay. So how we are going to calculate using this particular data. Okay. So in the subsequent videos, we'll see all these things. Okay. Right now, we'll get into the topic of conductance of electrolytic solutions. Okay. You know about the Ohm's law, resistance, right? For solids, we saw, right, in physics. So, what happens when the charge carriers are ions in a solution instead of electrons in a wire? So, that is the main part here. So, that is a major difference. Okay. So, same physics, new personality. There, electrons, free electrons in a wire. Here, the charge carriers, the ions in a solution. Okay. So we are going to study about conductance, okay, resistance, conductance, and so what is the resistance? This and all you have studied, right? For any conductor, resistance is equal to rho into L by A, where rho is the resistivity. So rho can also be written like rho is equal to R into A by L. Like this, you can able to write. So you know what is the resistance and resistivity. So resistance is ohms. So it is ohm meter. Resistivity is ohm meter, right? Unit for all these things. It can be in centimeter also. You can able to write. Okay. Then we'll see conductance. In your book, it is given as G, conductances. Okay. In physics, you have studied about sigma, right? Sigma is like instead of this, it is mho per meter. Right? Instead of ohm, it is mho per meter. Like that is the unit of the conductivity is. Here also we can able to say what is the conductivity. The conductivity G is equal to what? It is inversely proportional to the resistance. Okay. So that is conductivity here. See, ohm inverse, it is the unit of conductivity, or we can say mho. I told you, no. So ohm inverse or mho. Okay. That is the unit for conductance. And you can write this equation also in terms of here it is rho L by A. Instead of that, A by rho L. You can able to write. So this 1 by rho can be written as kappa. It is K, it is kappa. Okay, the symbol, it is a Greek symbol, it is known as kappa. In its unit, you can write the unit of kappa also. See here, okay, the SI units of conductivity or see in terms of Siemens per meter also we can able to write. So this is also very important topic you have to understand. Okay, so students confuse between, this is a common mistake I can able to say. Conductance. So this conductance is the property of this particular solution. So that is conductance with conductivity. So both difference you should understand. Conductivity is the kappa. It is an intrinsic property of the solution. It is independent of the cell geometry, but it is the intrinsic property of the solution. Okay, G is the solution's property totally. Okay, so G is like, we can say, so I can analogy with this. G is like how fast the specific pipe drains. K is how runny the liquid is itself is, like that we can take. Okay, so this is the basic thing. So G is like how fast the hose pipe drains the water. So this water or any liquid. This K kappa is how runny the liquid itself is. So that is the major difference. Don't confuse with this. Okay, the special unit for this is Siemens per meter. Okay, so Siemens per centimeter also we can write. See, this table, it shows the values of conductivity of some selected materials at room temperature, 25 degrees Celsius. Okay. So from the conductors, sodium, copper, silver, gold, iron, graphite, insulators, glass and Teflon. Okay. So insulators, you can see the conductivity is very less. See, in exponential of negative terms. Okay. So this is very, very, very important table. Okay, molar conductivity we are going to study about. First of all, you must know the conductivity. So, and then we'll learn about the molar conductivity. Okay, these are all molar conductivity is the star of this particular chapter. So, based on that, you are going to solve so many questions and problems. Okay, So then, this is for aqueous solutions. Okay, see the aqueous solutions, how the conductivity is. Then for semiconductors, how the conductivity is. You must know, for insulators only, the very less conductivity takes place. So its resistance is high. We know that, right? So conductors have high resistivity. When compared to aqueous solutions and semiconductors. It can be shown in this picture. Okay. So, the electrical conductance through metals is called metallic or electronic conductance and is due to the movement of electrons, right? The electrical conductance depends on the nature and structure of the metal, the number of valence electrons per atom, and temperature. Okay. Definitely, conductance decreases, okay, if temperature increases. See, for example, temperature increases, the conductance decreases. Okay. Now, this is ionic conductance. That is major difference between electronic conductance and ionic conductance. I told you about the analogy between the electronic conductance and the ionic conductance. The major difference is ions in a solution. Okay, there the free electrons in a wire. So that is the major difference. And this ionic conductance, basically, it is, we can say, electrolytic. That is ionic solutions. It depends on the nature of the electrolyte added, size of the ions produced, and their solvation, the nature of the solvent and its viscosity. In the salt solution, salt is a solute and water is a solvent. So nature of the solvent also involved in it, and its viscosity, concentration of the electrolyte, and then temperature. See, listen to this. If temperature increases, the ionic conductance also increases. This is the major difference you can compare with the electrical conductance and the ionic conductance. Okay. And one more point you must look into it, the concentration of the electrolyte also very important. There only the nature of the material is, okay, it depends upon the nature and structure of the material too. But here concentration also involved in it. So these are all the major difference between all these things you must know. Okay. Then we'll see how to measure the conductivity of ionic solutions. Okay. So you can able to measure. We saw, right? So sugar and salt water. Okay, but both look the same. But which conducts electricity, everything we studied, right? So the same here, how we are going to measure the conductivity of ionic solutions, all these things. Okay, so here it is given in your book what experiment it is given. We are going to study about the experiment. Okay, so let us move on to it. Okay, so there is a connecting wire. Listen to this very carefully. Two different types of conductivity cells. Okay, so what are the two different types of conductivity cells? Okay, I don't know what is that. Okay, so here unknown resistance, can be performed on a Wheatstone bridge. We know about all these things, right? We have studied already Wheatstone bridge in class chapter 3, okay, of physics. So you must compare always chapter 3 of physics with this particular electrochemistry, okay? Then, however, for measuring the resistance of an ionic solution, we face two problems. In electronic conductance, we can use the Wheatstone bridge to measure the unknown resistance. Here, for measuring the resistance of an ionic solution, we face two problems. The two problems you must address here. Okay. So one, firstly, passing direct current changes the composition of the solution. Okay. Secondly, a solution cannot be connected to the bridge like a metallic wire or other solid conductor. These two difficulties are there. What is the first difficulty? Passing DC changes the composition of the solution itself. Then how come you can able to pass the battery supply, power supply to that? So voltage through the Wheatstone. So in the Wheatstone bridge, you are supplying the external voltage. But here what is happening? Passing direct current changes the composition of the solution. So then what is the second problem? Second difficulty, a solution cannot be connected to the bridge. So if there is a connecting wire, we can able to connect with the bridge. But here we cannot do with the solid conductor. Okay, or see, for example, it's an electrolytic solution, not a solid conductor. So it cannot be connected with the wire. Okay. So how can we first resolve the difficulty, solve these difficulties? The first difficulty. Okay, it is using an alternating source of power. So the DC only changes the composition of the solution. So we can use this AC. The second problem is solved by using a specially designed vessel called conductivity cell. This is the conductivity cell. So several designs or anything is available, but this is one of the conductivity cell. Okay. So in this, you might have seen the platinized platinum electrode. So platinized platinum electrode. So what is that platinized platinum electrode? We have seen already how the platinum electrode is, right? So platinum is very costly. So it is coated with the carbon black. So we saw, right, already. So, and then here what is happening? Connecting wires. Here only the connecting wires is there. So electrolytic solutions are filled in this conductivity uh, cell. Then the platinized platinum electrodes here, see, then connecting wires. This is also a conductivity cell. Okay, several designs and two simple ones are shown here. So this is one type, this is another type. First simple one, second simple one. Okay, basically it consists of two platinum electrodes. So again and again it shows. Okay, so R is equal to rho L by A. You know, R is taken as 1 by kappa, or kappa is taken as 1 by rho. Okay, conductivity and resistivity are inversely proportional. And the quantity L by A is called cell constant, denoted by the symbol G star. Okay, it depends on the distance between the electrodes and their area of cross section, and as the dimension of length inverse, right? If it is L by A, meter by meter square. So it is meter inverse. So dimension of length inverse, and we calculated if we know L and A. Okay, measurement of L and A is not only inconvenient, but also unreliable. We can't predict. Okay, the cell constant, why we can't predict? So we can able to say this is the cell constant. Okay, by measuring L and A is not only inconvenient but also unreliable, means you are going to measure the wall area of a liquid, right? So electrolytic solution is a liquid, it's not a solid. So it is very difficult to measure its length and area. Then the cell constant is usually determined by measuring the resistance of the cell. Okay, so how can we measure? By mechanically, it's impossible to measure. It is inconvenient to measure. So we can use what is that resistance of the cell. So the cell constant is usually determined by measuring the resistance of the cell containing a solution whose conductivity is already known. So for this purpose, we generally use KCl solutions, potassium chloride solutions, whose conductivity is known accurately at various concentrations and at different temperatures. The cell constant G star, what is the cell constant? L by A. It is then given by this equation. What is this L by A? We can able to understand R into K. So what is R now? R is equal to rho L by A. L by A is the, what is that? Cell constant, right? If you want to find out this L by A, you can bring this rho to the left side. So R into 1 by rho. So what is this L by A? L by A is the cell constant G star is equal to R into, what is 1 by rho? It is kappa. Is it clear for you? So I hope it's clear for you. Then, okay. So then you can see this molar conductivity and conductivity table of KCl solutions, where you already know its particular various conductivity values, right? You know this value at various concentrations. So it is easy for us to calculate what? It is conductivity cell constant. So conductivity of the KCl already known at various temperatures. That is the main point. Okay. So this is the conductivity of a kappa is So kappa for mentioning kappa, you can write like this, some stylish way. You can write like, or you can write like this. Anything you can specify in a various form. Okay, like this also. Okay, so this is kappa, that is the conductivity. So conductivity at various concentrations, it is given here. So this is concentration, okay, mole per liter, then molarity, conductivity, molar conductivity, everything it is given, okay. So compare with the solutions. You know, KCl, all the conductivity and molar conductivity of KCl solutions at room temperature it is given, okay. Siemens per centimeter also given, Siemens per meter also given. Molar conductivity is per mole you need to calculate, okay. So mole you have to divide, that's it. Okay, so see this temperature, see this topic, I mean, table. It's very important for you. Then, you know about the Wheatstone bridge, arrangement of measurement of resistance of a solution of an electrolyte. Okay, so once the cell is determined, cell constant is determined, we can use it for measuring the resistance. Okay, so first of all, what is the procedure? You must understand whose conductivity is already known. From that, you can able to find out the cell constant. So by measuring the cell constant, we can use it for measuring the resistance or conductivity of any solution. Okay, the setup for the measurement of the resistance is shown in this particular figure. It consists of two resistance R3 and R4. Okay, a variable resistance R1. We can vary the resistance here, and the conductivity of a cell. So this conductivity cell, it is specially designed, you know, and then here the connecting wire is. So this wire is connected here. Okay. Then now the Wheatstone bridge is fed by an oscillator O. Okay. So and then a source of AC power supply. Here the oscillator is taken, and then from that oscillation, that is AC voltage is generated. You're going to learn about all these types in AC, alternating current, in the next, in seventh chapter of physics. So we'll see that. Then here, okay, what is that AC power in the audio frequency range? 550 to 5000 cycles per second. Okay, so it's an oscillation like, so 5000 to 5000, 550 to 5000 cycles per second, like that. Okay, then P is a suitable detector. Okay, where is P? Here. Instead of galvanometer, here P is connected. This is a detector, a headphone or other electronic device. And the bridge is balanced when no current passes through the detector. Okay. Under these conditions, you know the bridge balance condition. So use the bridge balance condition to find out all these things. Okay. So you know the stuffs, right? So this is basically all these. So R1 by R2 is equal to R3 by R4. Okay. So if you want to find out R2, you can bring all these stuffs here. R1, R4. This is the bridge balance condition. First, write the bridge balance condition. Otherwise, you might be confused. Even it seems to be very simple, but the students commit so many mistakes. Okay. So R2 is equal to R1, R4 divided by R3. So this is the way you can able to find out the unknown resistance, since R2 is the unknown resistant. Okay. So after finding the unknown resistance, okay, so what is that? Okay, the conductance or resistance of the solution in the conductivity cell. Okay. Once the cell constant, the resistance of the solution in the cell is determined, the conductivity of the solution is given by this equation. Cell constant, you know, conductivity we saw right now. R into K is equal to G star. So G star by R. By using this, we can able to find out the conductivity of the solution very easily. Okay. So this is the way you are measuring the conductivity. Molar conductivity is, you need to find out the molar conductivity with respect to its concentration. So that is the molar conductivity. Okay. So see here, the concentration of ions are eased with the ions move under a potential gradient. What is the potential gradient? We already saw like a slope you have to take. What is the potential gradient here? So number of charges, transferring from one place to another place, okay, with the potential difference. We saw that, right? So that is the potential gradient. So here also, how many number of ions are transferring, okay, with respect to the concentration, like that we have to take. So it is it is the molar conductivity. It is explained with it is designated by a letter, this one. This is molar conductivity. Okay. Kappa divided by C. In the above equation, if kappa is expressed in Siemens per meter and the concentration C, which is in mole per meter cube, then the units of molar conductivity is, so Siemens, so 1 meter gets cancelled, so meter square it will be, sorry, 1 meter square, then mole inverse. If you bring the mole to the numerator, it will be mole inverse. So you can able to understand. So it may be noted that meter square mole inverse, right? Siemens meter square mole inverse. 1 mole per meter cube. Okay, that will be 1000 liter. See here, per meter cube. 1 mole per meter cube will be 1000 liter per meter cube. Already you know about the mole concept. I taught you about the mole concept, basically, very basics of the mole concept in one video. You can go through it properly, then only you can able to understand what is the mole concept. So you can equate this to 1000 liter per meter cube into molarity. Molarity is mole per liter. Okay. And hence, what is that? Okay, this is the molar conductivity that is equal to, in terms of kappa Siemens per centimeter, then 1000 liter per meter cube into molarity. Molarity is measured in mole per liter. So with the unit you have to write, then only it will be tallied. Now check with the unit, Siemens per centimeter. Okay, it is, what is that? Liter per mole. So 1 liter and, per meter cube, 1 liter and liter inverse cancel. Okay, then mole becomes mole inverse. It goes up. Then meter cube will be, so you have to convert that into centimeter. So centimeter means you have to convert, right? So how can you convert that? Centimeter. So meter into centimeter. So 1 gets cancelled. Then 2 becomes Siemens. This centimeter power minus 2 goes up. So centimeter power 2 mole inverse. So this is the resultant. You know all these things. It can be calculated by using this relation. Okay. Some values are given. Okay. See this formula, this example. Values are given. Students, you must understand how to do the numericals very carefully. Here exponentials and numbers are given. Make sure you should not commit any mistakes. Okay. The digits are very important here. Okay. So calculate and find out. Okay, if you have any struggle in finding all these numerical calculations, let me know. I'll give you the tips. Then we'll see the topic variation of conductivity and molar conductivity with concentration. Okay, so all direct formula. If you want me to teach this, then I'll teach you this example. Then we'll move on to that. The electrical resistance of a column of 0.05 mole per liter. Okay, NaOH solution of diameter 1 centimeter and length 50 centimeter. So you know the solution is kept in a conductivity cell whose dimension is like that. Okay, its diameter is 1 centimeter, length is 50 centimeter. Okay, so it's length and diameter is given. Okay, so NaOH's electrical resistance of a column of this much mole per liter of NaOH is this. This is the electrical resistance of NaOH solution. That is R, ohms. In ohms it is given. Calculate its resistivity, conductivity, and molar conductivity. So first, students, I've always repeatedly saying to you, you must write what are all the given topics, what are all the given things, and asked. then it is easy for you to connect with the formula. Suppose if you forget about the formula or